audience is very less. Call all students. Who is there? Manisha? Yeah. Isko bolo. Telephone operator. Call all the students. So Dr. Jothiram Vivekanandan is a very senior scientist, Earth System Observatory, NCAR, Boulder, Colorado. That may be many of your dreams to reach sometime. His research and development includes polarimetric radar, which is very, very pertinent for our activity, dual wavelength radar, phased array radar, Lidar, and also microwave radiometer. So all these instruments IITM handles. Okay, so you will be our mentor, guide, supervisors. Okay, a philosopher, etc. He is a fellow of American Med Society, a great honor, an associate editor for Radio Science. And 2018 Christian Huygens Medal is awarded to Vivek for his pioneering and groundbreaking work on the microphysical characterization of clouds and precipitation using advanced remote sensor. This is actually many of our PhD students' topic, Vivek. we are, yeah. So it is very, very important. One example of his leadership are his development of a dual wavelength radar system created by adding a millimeter wave radar to the NCAR's S-band polarization radar, SPOL, which is very commonly known as, and his scientific and technical leadership to the development of an NSF-funded cloud radar of Gulfstream research aircraft. He made composing $100 million NSF mid-scale research infrastructure to airborne phased array radar. So this is a very big, I think, milestone. And currently working with this airborne phased radar team, and he has made many. He got many more awards and many, I mean, around this thing. So we welcome Vivek and eagerly waiting to hear your talk. And it is Professor. This talk actually series we started in honor of Professor R. Ananthakrishnan, who was a great mentor. Okay, was a great guide for the students. So we are very pleased and honored that you are giving this today's talk. 47th Professor R. Ananthakrishnan Colloquium.
Thank you, Father. Thank you for inviting me to give a presentation of Ananthakrishnan's Colloquium series. Good morning, Professor Krishnan, scientists, engineers, and research scholars. Today's talk, basically, I worked on this more than 10 years. In the beginning, a long time ago, I used to work on thunderstorms, where the hail and rain, the heavy-duty thunderstorms. After some time, once I did work on that, then this opportunity came up. The climate connection is more important, where cloud radars, aerosols, these are the most important thing. NSF realized that. Then they gave us radars and Lidar, which go on an airplane. Then I looked around in my institute whether these opportunities come rarely now because of new areas. Then I thought, well, I could move into this area. I did a lot of work. That's how I came up with this talk today. This talk has two topics today, two subtopics. One of them is about detecting particle types, the cloud, ice, supercooled liquid, droplets, using the radar LiDAR. That's the first topic. The next one is, okay, once we know the particle types, could you estimate liquid water content and the particle size? The next topic. And there'll be a two separate presentation, but they're all connected. Also, this applies to stratocumulus cloud. Stratocumulus cloud, most of you know, it's a very prevalent cloud type. It has a large extent. It has a cloud, climate, radiation background. It's a lot of important. This is covered more than 25-30% in a planet Earth. You can look at these are clouds, large extent, long term it exists. These clouds will transfer into rainy cloud after a few days. We have done studies like that. And how this cloud transfer into rainy cloud after a few days, that also studies has been done. And this cloud has a lot of importance because of its spatial extent. It lives much longer time period. We need science drivers for this. The cloud climate feedback, where we need W movement schemes, liquid water content, particle types, or particle size. These are things important. There are detailed measurements are done using aircraft observations in number of field deployments where they know all these things. But if you look at satellite observations, radar observations, they cover much larger area where aircraft not able to do that. Aircraft gives a very detailed, very good measurement, but remote measurements as a capacity or potential to do this. But how good we can do that? These are the key questions. This area is very well known. The cloud radar, LiDAR is not something new. There are about 40 years we're working on this, various techniques. I reviewed a lot of literature when we start working on that. What I can really do with NSF funding? That was my question. Said the dominant cloud types, where you want to understand this, stratocumulus cloud. Then can you improve the current estimate of particle liquid size and content, liquid water content in this case mainly? That is one of the main focus here. Currently, we use power law-based reflectivity relations. It's like a rainfall relations. You can have many of those. It works in certain time. It doesn't work other times. It's kind of works when you fine-tune it. Can we do a bit better than that? And that was my main intention. We can do that. Once we do that, then also we need a particle phase, the ice as a liquid, because that concept different. Radiative properties are much different. It's a frozen liquid part. For example, we did a study in Southern Oceans. Southern Oceans is a highly cloud cover. There's not much observation in Southern Oceans, where it's Antarctica and in Tasmania, south of Tasmania, we did that. And many times, the cloud models come up with a lot of glaciated output. But apparently, by satellite measurements, they know the supercool liquid exists there quite a bit. But that has to be really validated. And we did a program for about 2 months, got a good measurement, showed the bias in radiation studies in cloud model was resolved effectively because we got detailed in situ measurements plus radar and LiDAR observations. That's where we get a benefit. Okay, the two instruments we're talking about today is the cloud radar. Cloud radar is very good in the sense for airborne platform. It's about 95 gigahertz, 94 gigahertz, 3 millimeter. That means talking about cloud droplets are like 50 micron or even less than 100 micron particles are in a relay regime for that. And so that's very good. For cloud radar, very good. It does a lot of averaging, but 40 meter resolution in the range, you can get very high resolution measurement, you can get it. Then the LiDAR. LiDAR is a green light. It's a high spectral resolution LiDAR, HSRL. This LiDAR is different than most of you what used it so far. This LiDAR does the backscatter measurements. Also, it has 2 channels. That way, we correct for absorption. And so this LiDAR, high resolution LiDAR, it's basically when you do the measurement, the backscatter, what you measure LiDAR, is corrected for absorption or scattering in the atmosphere. And what you measure the actual backscatter measurement. And so then this has a 40 meter resolution. This has 7.5 meter resolution. The challenge is when you do the observations, the instruments have various resolution. Then we got to map that properly. It takes time to make it right, calibrate it right. It takes a lot of time to make it the right work. The right results to get out of that one. I have, in fact, in 2015, I completed the design of the cloud radar, wing part base. This flies on a Gulfstream jet. Gulfstream jets flies up to about 30 or 40,000 feet. It can much higher. It can fly above the clouds, quite a bit higher. I can close to the ground. It can fly the long range. The Gulfstream airplane. And they are mounted in a pod in a Gulfstream airplane. Then the LiDAR, it's the ice LiDAR, came from Wisconsin. This is this LiDAR in a cabin based. And there are 2 instruments on the airborne platform. And so I will use these observations for today's presentation, actually. Okay. In general, if you want to identify a particle or what type of, is it a rain versus ice, Based on reflectivity, we could identify that. Okay, the higher reflectivity, heavier rain, lower reflectivity is a cloud ice, cloud liquid. This is generally how we can do it. But these techniques are not valid all the time because there are cloud ice, cloud liquid. There are ice and liquid may have the same kind of reflectivity values. Since this threshold technique, threshold techniques have misclassification. In early 90s, there are 4 or 5 groups in the world, in US and Germany and Australia, mainly engineers who worked on the systems. They know electromagnetic scattering. They know how the particle behave. Only engineers know how to classify the particles based on radar measurements. The scientists don't care about it because scientists want to know, look, I don't want to know all the scattering complicated thing. Tell me microphysics. That is their need. But we know that problem existed. All these advanced lidars are built, but no request because scientists don't want complicated measurement. They want scientific output from that thing. Then I worked with Dusan Zernik, one of the very senior person in this area. Then Zernik and myself come up with a fuzzy logic-based method. This is much different than what we use it. In general, if you look at it, people talk about neural networking, classification, AI, machine language. These are methods where you need a lot of simulations, then train the neural network. I mean, this existed even 30, 35 years ago, nothing new about all the things. But think there's a limitation. In artificial intelligence or machine language, if something doesn't work, then either increase number of layers, number of neurons, the black box, that's a problem. Now things have changed quite a bit compared to what was there before, but still, there are some deficiencies. The technique, what I described today, is much simpler. It takes account of Lidar physics based on a fuzzy logic scheme. What is a fuzzy logic? Probabilistic method, fuzzy logic. Both characterize uncertainty between 0 and 1. It's the same thing. In a probabilistic method, a set and its complement. It's a null set, nothing there in between. That's how this Paul's method defined. In fuzzy logic, the set and the complement is not a null set. That's the difference. For example, say we take a rain and the ice, 2 different sets, rain, ice. Rain and ice not there. The intersection could contain melting ice particles, and it's not a null set. And so this is the beauty of fuzzy logic, where in nature, most of them have a continuity. When you get the ice, there's a melting, there's a liquid particles, and there is a continuity. Same thing happens many, like you got a heavy rain, the light rain, like that, drizzle like that. And so with this kind of situation, the fuzzy logic is a much better way to classify the particle types. We use the fuzzy logic technique, the technique what we published in BAM's cover page in 98, the Zernik. That's currently revived in many different ways. NCAR, this is the operational radars in all parametric radars S-band in US. They use the fuzzy logic technique for classifying particles. Then also for clutter identification. It has also fuzzy logic has other advantage. You could combine many types of observations, the temperature, DBZ, velocity, all to be combined in algorithm. It's not that you could combine only one type of measurements like that. And it has many advantages in a fuzzy logic scale. Okay. The instrument for this particle typing, I would be using the cloud radar, W-band radar, about 3.2 millimeter wavelength, then LiDAR measurements, then also the temperature reanalysis, temperature ERA5, you can use that. Then you got to validate. This stratocumulus cloud is not do anything on the ground because we can't capture the rain or ice, anything. It's all going to be in the atmosphere higher up above. That means we need to have some instrument we can verify these things when we say, is it liquid or ice? And that's what we use for a 2D 2DS probe. is about 1 to 1.2 millimeter. We use that probe so that we can validate what we came up with, the liquid ice, is that how good it is. That's the validation what we have. This is Socrates. I'm sorry. The Socrates field deployment where we had number search flights, about 15 search flights, each about 6 or 8 hours long. We had lots of data in Hobart, Australia. Basically, we collected in 2018. The thing is, we can collect all the good data set, the data quality, and merging the data sets, because these data sets are two different footprints. You got to combine them. It takes time. Since even though I worked on these models, like EM models and algorithms, still the data has to be right way so I can process the data to show how useful it is. Okay, the fuzzy logic scheme, the key thing is membership function. Membership function basically tells, say for example, in this case, I'm showing for the rain, the drizzle, the cloud, it's all very color coded. The red color here, the rain here. This is the DBZ value. DBZ values on the x-axis. This is a 0 to 1. That's all to it. It says, depending upon the DBZ values, like here, the rain basically after 0 DBZ, they're all rain possible. The cloud droplets, the blue color here, the blue is less than minus 15 dBz. Cloud doesn't exist here like that. Like that, we come up with the membership functions. This is the physics where you need to come up with a correct membership function, which are useful for classifying types. So in this case, similarly, we have for a Doppler velocity, the dipole ratios. Dipole ratios gives you information about the particles are liquid or non-spherical. For example, ice particles are non-spherical compared to liquid particles. And those can be gleaned from linear depolarization measurements like that. Then these are the radar observations. Then we have the LiDAR observations here. Again, dipole metal from LiDAR, backscatter. Since we could combine all these five observations plus the ERA5 temperature observations. Also, we drops on the airplane. We have those measurements. The temperature, for example, here, the temperature, I mean, it could be for a liquid, for a rain, or for a cloud droplets, or anything. It could be from below freezing to all the way to above freezing. And temperature could be anything like that. And these are the membership functions what are used in fuzzy logic. The technique is so simple. It's not that complicated. You have to go through a lot of complicated mathematics. You may think, because all the work is done in the membership function. This is the key, the physics, you understand. If something doesn't work right, that means membership function is not correct. We got to go back and tune it. And so we have a direct way we can understand how the things work. This kind of technique not only applies for our classification scheme, for many other physics you can use it, but I'm using it for identifying particle types.
ERA temperatures, how good they are?
Pardon?
ERA5 temperatures.
Yeah. I think at least for our observation, it comes after there's a lag time, right? We can't do it the same day. We have to wait. We used ERA5 temperature. Then we also drop stance and we have spot check. So far, it's good. But we are doing a very broad thing, below freezing, above freezing kind of thing. We are not going to detail about either how accurate it is. That is really good for our work so far. Otherwise, we don't have like oceans. We don't have that good a measurement. And if you look at maybe thunderstorms, then we can have a very detailed 15, 20 kilometer. But for this kind of large, we're talking about 40 or 50 kilometer. In that case, ERA5 temperatures are good for this case. Okay, the input fields are the 6 of them: DBZ from radar, velocity, backscatter from HSRL, temperature, 6 fields. Then output categories are raindrops, drizzle, cloud drops, small frozen droplets, large frozen droplets are melting. 6 steps, that's all. The 6 and 6 we have, simple thing. Then again, in this case, if the drizzle is below freezing, based on the temperature, we know it's a freezing drizzle, that's all to it, nothing fancy about it. Cloud drops, which is below freezing, is a super cool droplet, that's all to it. And so once we classify the particles based on temperature, we could say, is it super cooled or just warm process? It's as simple as that. The pre-processing is not that just because we got all the measurement, we used all the measurement all the time, not necessary. For example, Below the melting layer, it's all liquid. They're not going to be, especially small cloud droplets, no depolarization going to happen. It's all spherical droplets. We don't have to have the dipole measurements for that. If we could make it as simple as just dBc, we can use it. Hence, we can disregard some other thing below melting like that. Above the melting layer, all 6 fields are used because we have ice and liquid phase like that. Then the processing wise, like I was saying, membership functions quantifies how probable this particle for the given observations as the exist. For example, is it 50% or 60%, 80% time like that? That's what it is. Then we have 36 because 6 fields and 6 particle types, 6 times 6, 36 fuzzy fields we have. What is fuzzy? Measurements are deterministic because you measure a measurement, which is exactly like, okay, 15 dBz or 25, units. It's all deterministic. What is fuzzification here is, I showed the membership functions before, where we use that measurement, fuzzify the input. That's called a fuzzification because the fuzzification comes to membership function where it's overlap at the boundaries. That's all to it. And if you fuzzify the membership using membership function, a deterministic fuzzify, we do that. Then once we do that, then basically we have this weighting. There are some measurements have a less confidence. Some measurements better confidence. I know, like for example, Krishna asking temperature, how good it is. Suppose if we don't like the temperature, less confidence, I may put a lower, maybe weighting could be just a 10%, not 50% like that. I know backscatter measurements are highly calibrated, really good. Then I put higher confidence on that. Hence, that's the weighting we use it. Then this is a fuzzification, weighting. Just to sum, multiply and the sum, the QI. QI is one of those 6 particle types. Maximum of that one is, maximum value is likely particle type. That's all to it. It's as simple as that. These techniques are quite easy. It's not numerically expensive to do it. It's easy to understand. That's why it's been used in many of the radar. This fuzzy logic evolved from Japanese. How they use this, Japanese use this temperature controls because there's a long history to it. And based on that, it's a long history. And so we kind of used it for atmospheric purpose in this case.
Right. This predetermined weight that you were mentioning.
Pardon?
Predetermined weight.
Yeah.
To determine that.
Yeah.
How should be the time series? How long data needed to determine this?
That's right. And that depends upon data quality. We know data, look at it, then we know it's not that case by case basis, it's overall number for the project. That could be done like that. We know, oh, the instrument is functioning not good for this time, for few days. Then we don't even use that. Maybe put a lowest weight for that, like that.
If you have a good instrument quality data,
yes,
minimum how much data length is needed to identify this predetermined weight for different parameters? Oh,
okay. Yeah. If we have that, we don't. If we have how much data we need to predetermine weight like that. I think when data quality, if you know that good, I would say about 10 or 15 minutes of data is more than enough to do it. We don't need like a days and data like that. We don't need that much data because we are collecting lots of data. Like I'll show you some measurements. It's about each transect getting up megabytes or gigabytes of data. It's a lot of data there. About 10-15 minutes data because but we classify each pixel. That means each 20 meter resolution. It's not like done like every 1 kilometer. It's done every measurements done. Every 20 meter we know what the particles are. Then we kind of, because sometimes it's not a bit noisy, then we got to have some kind of averaging, nearest neighbor, few things you have to do it, make it better. That's all to it. But these are the problem. It's not problem. It's a part of the processing. Okay, this is a post-processing. We have 3 things ahead. Pre-processing, what fields we use it. Then processing is so simple. I just showed you multiplication and summation. The maximum thing that's all going to do it. Maximum thing will do that. Then post-processing, like here I said, right? Then say there are times we don't know the particles. Are they cloud ice, cloud liquid? Both look very similar because sometimes they're same, but our error measurements are not good enough to say. In that case, we just say it's a cloud. That's all. We don't know what it is. Just leave it at that because we don't exactly say liquid. And that is also possible because it's not all the measurements are useful sometimes. Some measurements are not that good sometimes. Okay, here is the result. I'll show you just one thing. On the upper left here, this is okay. This is bigger. The 5 minutes here corresponds to 40 kilometers of the measurements in an airplane. It's flying 200 meters per second. 40 kilometer Gulfstream flies. Gulfstream is flying about like this, looking down in this case. Now this is the radar measurement. This is the LiDAR measurement. At the same time, they're all on the same platform. We have these things are moving along. We have those things. And this is the DBZ measurement, basically. And this is basically Doppler measurement. You can see the rain falling much faster. This is the velocity here. This is the reflectivity here. And the velocity, when it's melting, it's falling much faster here. Then the dipole measurement is the melting layers here like this, like that. This all correspond to radar measurement or cloud radar in this case. Then these are corresponding LiDAR measurements. The LiDAR doesn't see below the rain, doesn't see much. See nothing here. Here we have radar, but LiDAR doesn't see much because get attenuated by strong precipitation. Then this is the LiDAR, dipole measurement here like that. Then this is the temperature measurement. This is the ERA temperature. See that the black line? That corresponds to the melting level, 0 degree isotherm. Now, with this as the input, then this is the scientific product where we have a rain, supercooled rain, drizzle, supercooled drizzle, cloud liquid, supercooled cloud liquid like that. Look at it. See here, this corresponds to drizzle, supercooled drizzle. This is the melting layer here. That's the melting layer here. You see that melting layer below the rain. This is a drizzle. This is a rain. This corresponds to cloud liquid. See, cloud liquid corresponds to basically very low DBC values, like that. And see, that corresponds to large DBC, the rain particles. This is the large frozen particle. It could be snow, large frozen particles. See, this one, the pink color here, magenta color, super cool cloud liquid. In the field deployment in Socrates in southern Australia, the interest was how much cloud liquid, cloud ice exists. That is a key mission they want to do it. So they can calibrate their many of the model runs. And they are looking for this kind of observations like that. Super cool cloud droplets, drizzle droplets, and ice particles. Like these are basically small frozen particles, small ice particles like that. This is one example.
One transect, is it?
Exactly. Yeah. You just airplane flies, taking the measurement just like that. Yeah. Yeah. Like that. It's only 5 minutes. Like that, we have about 6 hours each time, about 90 hours of data we have like that.
How much distance was there?
In this distance, from here to here, it's a 40 kilometer. It flies at 40 meters per second. Sorry, 200 meters per second. And it's a jet. It flies so fast. And a 40 kilometer from this end to that end for 5 minutes, roughly. It can fly very efficiently because of the ocean. And sometimes if you ask them to fly, could you fly just 100 meters above the ocean? They can do that. They get a clearance for, they can fly 100 meters ocean, they can look at it like that. Look at it. And these jets are very efficient, get the measurements where we needed to get it. That's why
it was 2 kilometers, is it? About 2 kilometers above the.
But yeah.
It's flying at 2 kilometers elevation.
In this case, yeah, in this case, it's flying after about 2 kilometers because closer they get a better sensitivity, instruments wise. Typically, it will fly up to 12 or 30 or 12 or 10 kilometers. It can fly even that high if you want it. But in this case, yes, close to 2 kilometers flying like that. Yeah.
Even over land, you can have this.
Yeah, yeah. Because our LiDAR is eye-safe LiDAR. It's not a problem. And that's why it's called, basically, it's a green light. It's the light, that green light is, it's okay to use it over the land. Then our radar is not that high. And so we could fly over the land or ocean. Yeah, these things could be done. Yeah, yeah. So,
what is the temperature range below 0 degrees?
Oh, here, that is temperature you see here. That I think you can read properly. This is 0 degree isotherm. this should be much cooler, I guess, maybe a minus 35, minus 40, I guess. Yeah, I don't know, maybe 20 or something like that. This all below, this all above freezing. That's a 0-degree isotherm I'm showing like that. This from reanalysis data, what I'm showing. Okay, like this, we did this product. I think Tara might know Greg McFarquhar, and he was a PI for this. And a number of PIs, he's one of them, Greg McFarquhar, one PIs. And he's a cloud probe expert. He knows how to decode any other cloud probe. Then he was so fascinated when he looked at this data. He said, wow, I can look at this data so much. He had about 3 or 4 students working on the data set with us so that he could validate his in situ observations with what we did with the remote observations. He was so fascinated because his background is in situ observations, cloud microphysics. And when we showed this data, he was so excited to do work with us. Okay, how do you validate? Okay, this is a validation. In this case, this is again a height. This is a distance. Again, it's about in this case about 12 minutes of data, much larger data. This is the DBC values. Then this is the corresponding particle types, like I showed you, rain, drizzle, the supercooled droplets like that. Then this is aircraft track. Aircraft track is that one. Then the 2D stereo probe, what we had. That's simplest to probe what we had. You can look at between up to about less than 1.3 millimeter, I guess. That's all can capture. Based on that, we computed. We can't validate all these particles. Very complicated with so many things. All we did is, could we make it just liquid and ice? Make it simpler, melting. That's all we simplified the whole thing because we don't have airplane flying into the cloud. Usually they don't fly about 25 degrees. They don't fly into the cloud. And there is a distance there. Then we did melting, liquid, and the frozen. We simplified the whole thing into just 3 categories based on what we did, so that we want to make it as good as possible, as easier for us to make it simpler to compare. Then using that 2D, the stereo probe, we computed liquid fraction. One means fully liquid. This is ice like that. You can see the red kind of coincides, blue and blue like that, red coincides. That's all it is. And so the comparison, this is from the aircraft. Then this from the remote observations. Kind of compass. That's all we have. And
the aircraft flew above the cloud, right?
Correct.
So how do we get any cloud probe measurement?
Yeah. The cloud probe measurements are, there are some clouds which are not shown in this. Very thin clouds do exist, and they're not shown in because to make it easier to visualize. And also there's a displacement in space-wise. This is 100 meters because not the radar, when it takes the measurement, it takes a while to get the measurement. And there are some differences. But in spite of all these differences, I'll show you the result. That's why Greg McFarquhar said, wow, this looks really good. I'll show you why it is. And this is a comparison. The result basically, the fuzzy logic method I described, the 2D stereo probe was used to validate the thing. 70% with in situ probe comparison. When we did in the 90s, the hail, grapple, rain, we have on the ground, we have very good ground truth. We can validate very good because we know what we are seeing from the cloud. But in this case, very challenging. We don't have a in-cloud measurement to do that. Very limited. And so with this, able to at least to show, yes, it does do that thing. But we have satellite measurements also. Satellites will pick up the cloud ice, cloud liquid like that. There's some validation could be done. But I focused only on in situ measurement and remote radar observations. This basically takes up the first part of the talk. The next part, I will use this to go into, yes, yeah.
Unique aspect in this observation is that there are ice below and water above, right? The supercooled water above the ice. Yeah,
That's right.
Indeed, it is very much challenging to fly in the supercooled water because it will get indeed ice.
Right.
also the observations. So how was it possible to conduct that? Whether the aircraft flew in the
Yeah.
verify that?
Okay. Yeah.
Like in situ or size distribution or the
Yeah.
Images.
That's right. I think NCAR pilots are a lot more experienced flying into what places. Before we fly into that, they give us a icing forecast, whether it's light enough to fly or it's not good enough to fly like that. And based on that, they're able to do some of the measurements. They also collected, we have some, Socrates as a BAMS article, they show the icing probe, how much ice icing. They collect icing also looked at because that's on the key measurement exactly. And there are times they collected key icing measurement, they're safe enough to do it. I haven't flown like that, but looks like those people know where to fly, what collected, and they use that super cool droplets, whether it's good enough for the research. Yeah, they did that. Yep. Yeah. Yeah. Now, okay, the problem with using reflectivity. Okay, I'm sorry. Go ahead. I'm sorry. I didn't hear you.
The previous slide.
Yeah.
Seems the melting layer or 0-degree isotherm is very low.
In the stratocumulus cloud, yeah.
But how much it is consistent in this region, right? Tropical region will be very high.
Yeah, that's right. Yeah, that'd be 5 kilometer tropical regions. Yes.
At the same time, you have told that if we take the measurement,
yeah,
if it is not lower, the accuracy will be again disturbed because of attenuation.
Yeah.
So how we can implement this type of observations in tropical region?
Yeah. I'll show you the two papers. The end of it, I have some reference for that. Then I'll show you how we can correct for that. Yeah, we have to do the correction because it's highly attenuating this thing. So we have to correct for that. Okay, thank you. I'll show you the paper. A lot of details in that. I'm missing other things because lack of time. Okay, here. This problem is very well known. The 10 micron droplets give the same reflectivity as 100 micron droplets. This is a problem. We know the problem very well. Kane 2008 paper, you look at it, it shows this is a problem because for a given liquid water content here, it could be minus 30 dBc here like that. It could be large dBc. Yes, using reflectivity alone, it's impossible to come up with liquid water content. But still, it's not that everyone has a very sophisticated radar and lidar. They use some kind of power relations to go with that. But we know the problem. This is the problem what we have. Liquid water content, 100 micron droplets, 1,000 of 10 million 10 micron droplets. This is very well known. And this is the problem what we have because of the D6 scattering, the LA scattering. That's what happens. Okay, the same thing. I'm showing you with the drizzle droplets, cloud droplets. This is basically the drizzle droplets, the cloud droplets. Liquid water content is much different. The reflectivity is much lower here like that. And reflectivity for drizzle much higher, same liquid water content. This is very well-known problem. To solve the problem, we got to use the LiDAR, other observations to do that. This is the current, what do they use? Before I published the paper. These are people have done it for many years, more than 30 years. We looked at it. Other power law relations. They use basically liquid water content, functional reflectivity, Atlas, Fox and Illingworth. Now, various people have the various, A and the B. They use that one to come up with that. Again, we have to threshold it. Less than some dBc values, use that. Get some dBc value, use that, and all those things. All thresholds you have to use because this illustration doesn't apply to all the dBc values. You have to be careful where you use it. Even then, the confidence are very limited. They also know that, but we don't have we have limitations. We work with what we have. Then again, the particle size. For small particle size, the shallow cloud, they can estimate something like that. That's all. I can't do that. My objective in this paper is, could we do that without all those restrictions? Can we do it? Then other thing is, can you extend it without worrying about these thresholds like that? dBc is something small and large. Can you do like that? That is my objective, how we can do it. I'll quickly go through this one. Currently, like I was saying, it assumes a mathematical model. It's a gamma or exponential distribution like that. I lost my green light. Okay. Then it's artificially partitioned. With that 50 micron, the cloud droplet, everything has to be somehow we have to assume. Otherwise, we cannot work like that. then valid only is restricted range of radar observations. It doesn't apply to large observations like that. Okay, to do that, we need a detailed electromagnetic scattering model. I may not go through this one. And here is the the left side, what you see is for radar, the relay scattering the blue line. Then the right side is the Lidar backscatter. These are the things. I have done a lot of computation for radar. Lidar haven't done that. The problem with the Lidar is in the Lidar frequencies, the absorption is almost zero. Hence, this keep on resonating forever. It won't converge. Values won't, because it's absorption, the photons won't converge. It took me many months to do the computation. I sent it to experts, asked them why it is like that. But they say, well, that's how it is. Then I got to ensemble averaging, come up with how we did that. The right side is a Lidar backscatter. The left side is a radar backscatter. This is like input to a scattering EM theory model where I can do that. Then I use the we had the interesting thing is the VAMOS is a 2008 experiments conducted where the C-130 flew into stratocumulus cloud over the South Pacific, the South Pacific Ocean. They collected a lot of very good measurements. The C-130 went up like this and down like that. They get a profile they collected. So gold mine of data set. But I thinking, I did not know this. Then I started simulation. I asked a person, Jon Jensen, he's expert in that. He said, well, Vivek, do you want this? He said, yeah, come on. Very good data set, quality control. Every 1 second, they got this data set using cloud probe, diesel probe. Every 1 second. I got 4,650 1-second droplet spectra. The ascending and descending passes like that. This is a fantastic data set. I used that one to simulate stratocumulus cloud. In the paper is detailed, it's not given in the paper, how I come up with that technique. And that was very helpful because in situ measurements are key. With the EM electromagnetic scattering models, we can do that. Now, many other people, or most of the people work on in situ measurement, they think about median volume diameter, or, many of these things are very common for them. But for a remote sensing person works on radar and Lidar, it doesn't work that way because we're not doing an in situ measurement. We are doing a radar and Lidar measurement. We got to define something which are consistent with our measurement. And what we defined, it's not something new, I defined it. Even before people are using this one. This is basically a radar. The Z is the radar measurement. Beta is the Lidar measurement. Ratio between two observations, both the radar and the Lidar, that independent measurement, because one is a D squared optical scattering, D squared, as the D6 relay scattering. The two different measurements. Use that one, define a size called RLED. RLED is basically a droplet size of that volume. That could go anywhere between 3 micron up to 500 micron. Doesn't matter depending upon. You're able to get a size. Remember the particle I showed you, the previous I showed you. If you know the particle size, the cloud or drizzle, then you can estimate the cloud liquid water content or liquid water much accurately. That's what it is. Hence, it's a droplet size. Then that is liquid water content normalized with the droplet size. Then you can do that. Hence, in summary, the technique is so simple. We got two measurements: radar measurement, cloud radar, radar measurement. Take that ratio. This is, see, the interesting thing is if you go back here, see, this the left side curve, there's no scatter at all. There's a reason for that. Because I defined exactly how it should be, so that there is no uncertainty. It's like a physics. That's all to it. Hence, it's a deterministic measurement of a particle size using two remote observations. The left side, right? Then the Z is normalized with a size. Liquid water content is just a simple relation. That's all to it. With that, we did that liquid water content. Now,
this is also from aircraft.
Yes. Yeah.
So in ground based, so we have a cloud radar.
Yes.
And we have a microwave radiometer.
Yeah.
So I think we can do that same thing, right?
Similar thing could be. Even with this, there are various ways you can. Cloud radar you have, yeah, we can do that. But we need Lidar measurement. That's better. In this technique, is Lidar measurement. You don't have Lidar. But if you have any other Lidar measurement, we could use that. But if you have radiometer measurement, there's a way we can do that. I can describe to you. Yeah. Constraint could be done.
Previous.
Yeah.
That size is proportional to the ratio of the two.
That's right. That's right. Exactly. On the D6, the D squared, that's the fourth power. Hence, we got a 1/4, 0.25. That gives a micron. It's a kind of scaling problem. That's all to it. The D6, D squared, that means something about D power 4. Take it 1/4 of that one, 0.25.
That shape, how did you get that?
Yeah, that shape comes with the simulation. Remember, I showed you 4600 droplet distribution. These are those points. Yeah, it comes like that. Yeah, it's all it's in situ measurements. That's what this is. It's a fitting in situ measurement. It's perfectly defined this way. It's a particle size. Yes, Tara.
Now this is very well correlated with LW.
Oh, this LWC, that's right. I'll show the result exactly. I'll show the result why, because I can't show one instrument, I can't show everything is right. I have a deep independent measurement, I show, like a radiometer, I have to show, yes, it does make sense. I'll show there is a real soul in few slides. Yes, I have to validate that. Yes, Tara? Yes. Yes.
Between the cloud droplet and the drizzle.
Yeah, it goes, in this case, it goes up. Yeah, that's right. It goes only up to the 180 microns. That right? Yes, yeah. It can go up to even higher, little bit. 180 micron, I thought less than 50 is the cloud droplets, above 50 is like cloud. And mostly it does work for this case. And so I'll show you the RLED. We don't have a RLED validation. We have to fly into the probe and do that. We haven't done that yet. But liquid water control, I'll show you, which is the end result of all the things. I'll show you liquid water, how good it is. Yeah, we have, in this case, okay, I have to clarify. Yeah, at CFA we can do that. This measurement is done in, actually, I forgot to mention. Remember, I said that I got this I got the data from VAMOS, which is the Southern Pacific. Where I applied this one is a Northern Pacific CSAT, where the cloud systems and trade winds. That's Bruce Albright did that after many years. 2015 did that. And the technique, what I used from Southern Pacific, the physics is same, but applied to same type of cloud in a warm cloud in Northern Pacific. This is between Sacramento and Hawaii. And we applied. It still works.
John Stevens and other people were also looking.
Graham Stevens? Yeah.
John Stevens.
Beyond, that's right. Yeah.
Barbados Cloud Lab.
Of the coast of California. And
oh, okay. Yeah, I think there are some people looking at some of the data sets, but that's right. Yeah. This is like a Northern Pacific, the persistent stratocumulus cloud. You want to look at it, and this
you get similar result there also.
Yeah, that's what it is. This what actually my observations came from Northern Pacific. I applied whatever I developed, the technique what I developed Southern Pacific based on simulations, in situ probe simulations. I took that, applied to Northern Pacific. It does work because physics is validated that way. It's not something like it works in Southern Pacific because some climatology, some issues, not nothing like that.
This is the gamma distribution. Because of some.
I would say, in my case, the algorithm, it doesn't depend upon whether it's a gamma. Gamma is a mathematical description of something. That's all you're going to say. Unmodified gamma or Marshall-Palmer. Everything is our mathematical fitting. And I'm not a person like a Greg McFarquhar. He is very good in all the fitting. I haven't done that. And my interest was, okay, I'm not worried about whether it is truncated, it's a bimodal, anything. I didn't bother about it. I didn't even verify that. Also, we don't have detail. We have some measurements of like a 2DS probe and a cloud probe. I haven't looked at that. John Jensen retired. We don't have the data, but we have some data. I haven't even compared that, how good it is. Okay, that's the equation. Okay, this is the result. What is in the top is a radar measurement. The LiDAR measurements. You see that LiDAR measurement, I don't have pointer here, I'm sorry. This pointer went away. I got to have a pointer to show that. Yeah, this. We have a 4 panels here. The bottom two panels are what we retrieved. In the top two panels are what we inputted. All inputted is radar and LiDAR measurements. That's all to it. The bottom two panels are, one is the size, micrometer, other is the liquid water gram per metric cube. That's all it's showing that. This is the end result. Then we got to validate that. Then you see that there are some drizzle falling to the ground. In the top panel, if you show that, there is a dark line, if you see it, close to zero above that. That's 100 meter. That are looking at the top like that. They're flying at 200 meters per second over the Pacific Ocean, looking at the top. There's a reason for that. If you look at that from the bottom up, thank you. Very good. Okay, that's a DBC measurement. This is a drizzle falling to the ground here. Aircraft track is right here, like this. These are various cloud types here. I'd see it. This is a LiDAR measurement. See, it's a cloud base here. Cloud base. Now, when you retrieved it using the algorithm what I showed you, see that these are very small droplets, less than 20 micron or 10 micron droplets. It's logically consistent how it should be. The LiDAR measurement, right? LiDAR measurements like that cloud base, see that cloud droplets like that. Then the big droplets here, that corresponds to drizzle droplets like that. Then where the cloud liquid exists, remember I showed you when the lot of cloud liquid exists, the cloud droplets exist, cloud liquid is large, 0.2 gram per meter cube here. Large cloud liquid in the cloud top. But these are warm clouds. It's not cold clouds, warm clouds. And logically is consistent. But still, I can't publish this work logically consistent. I have to show something else to make sure that's correct. I'll come to that. And so we can retrieve droplet size. This RLED related to median volume diameter or effective radius. I can do that in the paper. I described how to do that. You can relate to it because some people interested looking what it means. Median, you can do that. Not a problem. There'll be some scatter to be there. Okay. Okay. This is a quickly I go through that here. Suppose if we don't have a LiDAR measurement, see this is a particle size. We don't see a particle size is here given like that. But looks what compared to this particle, it doesn't have that good resolution with our LiDAR measurements. It's washed out. They're only radar measurements only. Then if you liquid water content, next one, here, I don't see that thick or intense the cloud base where a lot of liquid I showed in the first one. Hence, having the radar helps to make it even better. This is what you get only using the radar. Okay, where is the validation? If you do all the work, want to publish it, validation. Here it is. There are two lines here. One is the radar and the LiDAR, which is the blue line. This one's the blue line here. This again the same, the 5 minutes I showed you, 40 kilometers of distance where it traveled. You have a radiometer looking the same thing as they fly. Radiometer, radar, and LiDAR, all three, right? Then the red line here, see the red line? This is the radiometer. That's 183 gigahertz radiometer liquid water path. This is the path, what I show here. Total liquid in the cloud. See how good it is. Now, if you look into it, it's amazing. The footprints are different. Radiometer footprints are much different than radar footprint. Radiometer takes much longer to collect data set because radiometer takes a lot more passive signals to do that. Active measurements are much faster. In the time difference, the space difference, in spite of all the differences within the cloud, we are flying so one transect. And with all these things, we're able to get such a good correlation with independent. One is the active measurement from radar LiDAR as a passive measurement, independently verified it. In fact, pardon, yes.
Radiometer is a ground-based radiometer?
Pardon?
Radiometer is within the flight?
Yeah, no, it is mounted on the airplane. Yeah, it's from pro sensing, yeah. And the Tasmania has the radiometer, yeah. Now, these are all the same flights, how flying the ocean like that. So you're able to get a good comparison like that. And so we're able to validate. In fact, when I looked at the radiometer, they warned me, Vivek, don't look at the radiometer because when there is a precipitation falling on the radiometer, there's a bias. And also, radiometers are not well calibrated. Many people said, discouraged me. I said, well, I don't have a choice. I need to validate my data set. But luckily, this worked out okay. And sometimes you have to take a risk. You have to look at it because the instrument developer might say many things because they have a whole many other parts they're looking at. But take a chance. But this really worked good. And so we have few cases where we validated like that. So anyway, looking at it, we were able to validate liquid water content as good as we could within this, with the 2 independent measurements on an airborne platform.
This is the advantage if you would have flown above the cloud and down, down looking white.
Yes. Remember, I showed the previous picture was above the cloud. It doesn't see much below the cloud because LiDAR gets extinguished right away. If below the cloud, if you look at it, then in this case, you're flying very close to ground, looking up. Above the cloud liquid you can see with the LiDAR. Then also I showed you the drizzle and everything like that. It's all, when you fly from the ground, looking from the ground up, actually get a much better coverage of LiDAR observation compared to looking at the top.
The other question is,
yes.
You said 183 gigahertz.
Yes.
So what about in the K band if you would have used?
The Ka band?
K band radiometer?
We could have used the K, we could have used, I think this was, because this 180 gigahertz is a much higher sensitive radiometer for small liquid. These small liquids are, like, if you look at it, liquid water pairs are much lower, right? Like 0.5, 0.3, like that, much lower. That's for that is very good.
183 gigahertz.
Very good for that, yeah. For high sensitivity, because very high frequency compared to 30 gigahertz, talk about. Typically use a 20, 30, 90 gigahertz radiometer for cloud, vapor, liquid, like that. That's what typically used. But 183 is much more compact on the airplane, like that. We can do that. Okay, this summary slide. I'm sorry, I'm going a little bit over time here. And okay, the key is, see, it goes between -0 dBz. Previously, I showed the results. People use it about 10 dB. That's it. They can be -17 to maybe like a -25. That's it. Or something -20 to -10. But it's much broader. 0 dBz. Why above 0 doesn't work? Because Mie scattering is set in a W band. Mie scattering is W band 3.2 millimeter wavelength. Anything about 300 millimeter, particle size become Mie scattering at a certain size. That's the problem. This is very large dynamic range compared to what currently technique was described in the literature. The using the simulations, using the DST spectra, then accuracies, right? See, you can get very, very precisely size and gram per meter cube like that. Because these liquids are very small, start with 2/10 of a gram. We got a very good accuracy to do that. We can't have a big error margin. That's why this is important to do that. Then see the Southeastern Pacific, where I collect the in situ measurement, up Northeastern Pacific, where I really retrieved it. The physics is preserved, whether we go from one to another, as long as you got a solid background how we did it. Then this bottom up water for a cloud and liquid crystal water like that. That is my last slide. This is a citation slide. If you're interested, the radar I worked on to develop, I conceptualized, I developed it for a number of years, the cloud radar. We bought the parts, we assembled it in NCAR, the W-band radar, put on the part, that radar. Then the paper was described, the second paper here describes detail, all the equations. You can look at it. And if anyone wants to have any simulation program, anything like, let me know. I have all the codes because I developed it many years. Then the particle ID type, fuzzy logic, was published in this paper, 22 recently. And so I mentored the person like that. And it's the technique what developed today, described today, I'm sorry, it's quite simple, physically intuitive, want to apply it. That way you could use it if you're interested in doing like that. So I would stop here. Any other question?
Is the same person who worked with Robert House?
Correct. Yeah, she did some satellite-based research. That's right. She came to NCAR, data manager. Now my job is to mentor other people at this point because I have done enough work to go with that. And so she's under fuzzy logic. She said, wow, it's quite simple. She bought the ERA5, temperature, all that. She's very good in pulling the data and analyzing data. It's like a very good math lab. The people we need, the kind of people who are very good in software skills. Otherwise, we can have all good ideas, but we got to implement it.
So, yeah. Excuse me, sir. Yes. Okay. Thank you, sir. Thank you for very informative talk, sir.
Okay.
Just I have some basic question.
Yeah.
Like there is the directly equation which you have shown.
Yeah.
It is formulated based on the Lidar backscatter as well as the radar reflectivity.
Correct.
So this particular application, because you have mentioned that you have used a HSRL, it's a green Lidar, which is likely to be NDR. So what is it is a 500 to 532 nanometer, like
0.33 micron.
okay.
Yeah.
100 nanometer.
Radar is highly calibrated.
Yes,
That's not niche. Okay.
Yeah.
Radar, it is highly calibrated. Absorption. That equations are given in the paper. How I did that. Yes.
But the attenuation depends on, suppose, like a 500 meter size. The VV size, suppose the 500 nanometer wavelength, the VV size, and the size of the particle, which is a 3 millimeter. Their VV size is totally different. How we can assume so different wavelength to, because it is one is my scattering, which takes place in the scattering. So how we can match up those things?
That's right. We're not matching any other measurements. We are trying to get independent measurement because once a because different measurement is not useful to me. Lidar is a D-squared measurement. Radar is a D6 measurement. That way we have two independent. That means the radar, what I'm looking at is small cloud droplets, D-squared. Radar looking at a long tail of the distribution. That means you got two different measurements in a spectrum. That way, we got two independent measurements to characterize microphysics. And so we need to, in the paper, I'll show you how different LiDAR is. If you look at the radar, as LiDAR measurement plotted, the only correlation will be total independent measurement. That's how we need to have it, like a radiometer, total independent measurement. We need to have independent measurements. Then it's useful for you to retrieve more than one variable, because I'm retrieving two variables here, size, liquid water. Need two independent measurements you need.
That's what's okay.
Thank you.
Thank you. Very nice and informative talk.
Yeah.
So I'm a little bit curious that more microphysics that classification is something different what you have mentioned.
Yeah.
So what is your suggestion how we can use that verification of the model? Because basically the densities, it depends on the hydrometeor density. So here, this is fuzzy logic based what you are telling. So how good it will be to validate the model product with the observation? This is first one.
Yeah, let me answer first question what you got. If you want to the fuzzy logic scheme for like a C-band radar, X-band radar, which we have it here, for that, all the membership function showed you about six particles I showed like that, each other six like that, any number of particles, right? Those membership functions are well defined. Okay, you could implement it. In fact, those things are available in some other software tools, exist already, and so you can use those. Membership functions exist already. This has been done past 25 years now. The cloud radar LiDAR, which is new, and for that we have the, like I showed the curves like that. And so this applies to, as long as we understand the physics, then we could tune those membership function says degree of, this particle, how close to that measurement, like a reflectivity or the temperature or the Doppler velocity like that. And how close is that measurement? That's membership function. Membership function has to come from physical intuition, and there is no equations for that.
Yeah, so means from the model, so we can get the reflectivity and translate using your fuzzy logic technique to classify the model hydrometer.
If you have cloud model, it generates let's say your mixing ratios, right? You get all the things. There's a program, some of you are using the CR sim, cloud solving simulator, like that is a very detailed model where you with a lot of input, or you can look at any of this model output, then it generates your radar fields. Yes, we can use that. We can do that.
Okay.
That's a very good way to do it. We don't have in situ measurements.
Yes, it will be very nice. Thank you so much. My next question is that you said that density is very important. And if we go for the single moment to double moment and triple moment, so how we can, as it is the sixth power, so can we use the sixth moment to introduce the reflectivity as a metaphysical scheme?
Okay. If it's the Mie scattering is the problem, we cannot do it. D6 applying Rayleigh scattering. It's small particles compared to wavelength for 3 millimeter 0.3 millimeter particles are okay. If it's like 1 millimeter, then it won't work. Then you need to have a detailed electromagnetic scattering mark, and me scattering, you have to use it. Also, spherical, non-spherical particle makes a difference. And so this involves good amount of EM theory. That programs exist. Is that we have to do anything. It's all programming. The only thing is you have to understand how to use it right. And it will take a little bit time, not a whole lot of time. Nowadays, things are highly modular based. It depends on how much passion you have to understand and work with. That's all to it. Yeah, this program exists. Yeah.
Okay, thank you, sir.
The CRSIM is a good program. You can use it. Also, Oklahoma has one more program like that, simulation program like that. Also, a number of people have some other programs like that. Yeah. Yep.
So thank you. Excellent talk.
Thank you very much.
Excellent. I just want to start.
Yeah.
This CloudSat and this Calypso and all these satellites are there.
Yeah.
They're also working on the same.
Exactly. Same frequency. Exactly. That's why we build this kind of instrument to match. In upcoming, the Japanese satellite, they're all going to have this kind of Lidar. This radar is very, very, is going more versatile. It's going to be more common coming years.
So this two independent measurement is the main idea.
Correct. That's exactly. Because again, the LiDAR, I didn't show aerosol part. I don't know aerosol. There's not a aerosol. It does that. How do you characterize aerosol? Because the LiDAR is the key. Actually, I didn't show you more thing LiDAR. The LiDAR, the backscatter, also measures the optical depth in a visible wavelength. Then using that, you can characterize aerosol type, either sea salt versus something else, a dust. NASA has done this work. Hence, if you're going to get a LiDAR, the HSRL is the better LiDAR to use it because it does two measurements. Not only it's a backscatter, also it does optical depth measurement, attenuation measurement. And that is a key measurement for many of the studies in climate studies, optical depth. And does it optical wavelength, it does it. And that's also good. And so these are the upcoming instruments on the satellite platforms. Are mostly there are like W-band LiDARs or K-band. The HSRL, these are the things going to be. Yep. Already, like you mentioned, we are the CloudSat Calypso, same thing exists. Yep.
Yeah. Questions. General questions. It is nice.
Yeah.
So one comment, one question. Is that what you are saying is, what if I have understood a lot of stuff actually. To understand also it will take time. But what I am a little bit understanding is that, see, this one thing is radar and lidar connecting this, right?
Yeah.
And main is one of the ingredients is your drop size distribution, right? The question is what you are asking in connection to that and what you are telling that nowadays we have a what is called a cloud simulator.
Yeah.
So what you are telling, using this PID and other techniques, is something like radar lidar simulator.
Yeah.
Correct?
Could be done. That's right. Yep.
That's what I understand.
Yep.
So but even Bob House once told me that, see, this convective stratiform, what comes out from the model,
that's right,
and what we try to compare from satellite, it's completely meaningless.
It's not a big difference.
Because in model, convective means whatever rainfall is coming from the convective parameterizations. But here, it is derived based on some algorithm. They're completely different word.
That's right.
Okay, stratiform in model, we just compute what is contributed by the large scale.
That's right.
But here, the algorithm is completely different. So these two are we're comparing completely apple and orange. Doesn't make any sense. So to make it sensible, okay, at least it's a convective and stratiform, you have to make a simulator. Now many people are using that. This our CAM, CSM. It has a ready-made simulator existing freely available. Okay, all the data are compatible. Now for all models are not there. For example, WRF, one has to work on that. For CFS, GFS or other model, one has to work. But I think what we don't have, because see here you are actually measuring explicitly the top size distribution.
We did an in situ measurement, did that.
Yeah.
If you want to go from numerical weather prediction model to cloud model or something like that, we have programs now. The CRSIM will do it.
Correct.
Then we can validate.
Yes. So that's the point. Is that one has to run a cloud resolving model, one single column model, which resolves all these parameters. Then it needs an interface like simulator.
Right. Yeah.
then come to this stage where you get apple and apple.
That's right.
Then compare.
That's
So
right.
this is my comment. My question is, see here we debate a lot. So there is a WMO program now. R2O. They call it research to operations.
Correct.
What we debate here, observation to operations. O2O. It's not there in WMO. Still, we will come tomorrow. So my question is, see, you are engaged in NCAR for so many decades, and you have many of your colleagues engaged in very state-of-the-art observation. How much this O2O actually happened in developing models in GFDL, in developing a model in NCEP, or many other Department of Energy models? Is there any existing mechanism? Does it happen regularly? Or it is kind of left it to the individual scientists and centers? If they wish, they take your hypothesis. If they don't wish, they go in their own way. So, I mean, here we debate a lot, because before investing in radar,
that's right.
There'll be, there'll be question for administrator as well.
That's right.
How much of these will improve
to O2O or R2O both? Right?
If you can highlight in.
Yes, I would say, in like a Bob House, Ed Zitzer, the senior people, when they devise a program, then always there is either validate what the models are developed, validate using an in situ observation model. They have to do, otherwise they're going to get funding. There is necessity to do it. Then I got to connect with the previous research that show that. And I'm sure it does happen here also. There it's a lot more. I know the modeling wise, the Washington group, Penn State, Oklahoma, Colorado State, they are very main centers. I mean, they work closely with us, but still there's a big gap, the data assimilation, where modelers talk one way and we talk different language. And there is a big emphasis nowadays data assimilation, as we have to make it right, because data assimilation means you need to have a good data quality, people understand what it is, how do you implement all things like that. Otherwise, got a bad data quality, it's going to crash all your simulation. It's not good. And so, it is a challenge, O2O, but I can tell you one thing. Remember, I mentioned about $100 million project, what we're going to work on. It's unprecedented to do that as an electric engineer. I led that project description, to write that project description, and gave it. This is a phase the radar. The interesting part is, it's a 4-year or 5-year development program on a airborne, a tropical cyclone. That's the main key, what developing this one. Tropical cyclone, can you go over Atlantic to do the measurement for hurricane, typhoon studies? That's one of the main objectives. Now, NOAA said, we have airplanes which are going to retire in 2030 because there's a limit how long hurricane hunters can go and collect the measurement. 2030, NOAA funded us, you may not believe, more than $10 or $15 million, because they said they want to look at R2O directly, because they said it's taking too long for us, because they want to next generation, when they get the airplanes, which is going to be C-130, which is, I think India has a C-130, number of C-130 India has it. They're going to C-130 to get this phaser radar on their platform, look at tropical cyclone studies. Rarely happens, that kind of confidence someone has. We didn't even develop the radar yet. We are going to work on that for next 4 years, develop the radar. Then NOAA's interest. It's a rare thing. And so these are highly risk, because we haven't shown the radar yet. Because this radar, when you do it on a C-130, the key thing is it will do the very good 3D winds of cloud structures, including a hurricane, 3D winds, where you can a formation of rain bands, moat was active regions in a cloud. You can look at it. That way, we can characterize the intensity of the hurricanes. The Cat 3, Cat 4, that's the key, because the winds are key. But in addition to it, we got to the microphysics, it's a polarimetric radar. Non-diabatic heating is so difficult to do. Diabatic heating is easy to do. Non-diabatic heating, can you do it? And this is the first time one platform that can go to 3D winds with the microphysics could be done. How? Because the airplane is moving. Because of that, same platform, we can use a 3D. Otherwise, you need 2 radars to do that. But in this case, 1 radar can do it. And that's why NSF is interested for us to move forward to build this radar. We have to show, ground-based, they have done it, but we're doing the airborne radar. then this will be a quite innovative technology. To speak about AI, machine language, this is where you can apply it. Reason why it's active aperture. You saw one radar and described to you. The radar what you develop is a 2,300 individual transistors. That means got many radars embedded in a big 2-meter dish. That's called a phasor radar. Like you look at the traffic signals. It's not a one red light. It has LED lights populated. Same thing, same concept. Anyway.
Thank you.
Thank you, Vivek, for excellent talk. And he has been here for the last 2 days, and we are going to visit our testbed facility tomorrow onwards. So thank you for excellent talk. Now I request Director to felicitate Dr. Vivek with the Institute Memento.
Thank you very much.
Really, I enjoyed your talk.
Thank you very much. Thank you for your interest.
I learned a lot also from this. So this is a small.
Thank you very much. Thank you for
really
your
enjoyed it.
appreciate it. Thank you very much.
Thank you.
Thanks a lot.
Is there a second talk also?
Today is
No, there is another Weng Shaoli
is my colleague.
from NCAR.
He's a airborne scientist.
Okay.
And
He's going to give a small tutorial on dual Doppler.
dual Doppler.
Will be online.
Online.
It's just online only. He's in Singapore at the AOGS conference.
Okay.
He asked to give a talk here, so can initiate some interest here on 3D.
I'm trying to join if possible.
We'll try to record that in case I know possible.
Yeah.
In case I know you are going to be 5 o'clock. Your talk this time. Sorry.
No. I think this is very
Yeah.
good.
Thank you very much for taking your time.
Online that it is transmitted, no?
Something we could at least learn, get this idea.
Yeah, this is something I thought people say a lot of interest in getting a dynamic structure. I thought since you are getting radars.
Trimetation radar, that may not be having this principle, right? They
No.
don't have a LiDAR, right?
No,
That's
no,
a single
no.
frequency radar. Whereas GPM has a dual frequency radar.
Yeah.
GPM has this.
Dual
GPM doesn't LiDAR. Only 2 radar.
Okay.
Not for cloud microwave. It's only precipitation study.
So they don't have cloud.
Yeah, no. Only that